Hello friends, welcome to this new series of videos on the topic graph theory. This part 1 video will cover what is meant by trees and what are the properties of trees. It also will talk about quantities like spanning tree and minimum weighted spanning trees. Come on, let's get started. What do we mean by a tree? A graph which is going to be connectedless and which is also going to be circuitless will be referred by the name called as tree. So if this is going to be a given graph, say, we do see that there is going to be a path that is going to take us from any point of vertex to any other point of vertex, then we call it by the name connectedness. Okay, so if a path is available for moving us from one particular source to the other particular destination without any hindrance, there is going to be continuous alternative sequences of vertices and edges. That's what we refer as path. Then you call it as connectedness. And secondly, what do we mean by circuitless? It must not have a closed quantity like this, like closed path. Closed path meaning path that begins and ends with the same vertex, in which case the path will be referred by the name circuit or cycle. Now when we see this example, we notice that D, E, F, G, H, this is going to form a closed loop kind of structure. That is, the path over here begins with D and it is going to end with D. So this is what we call it as a circuit. But we need to keep in mind the tree is going to be connected and it is going to be circuitless, which means it must not have circuits. No circuits must be available. So this will be a classic example. You take any two vertices, you will be able to find a path to reach from anywhere to anywhere, in which case you call it as connectedness. And you don't have a path that begins and ends at the same position, forming a circuit over here. So this will be an example for your tree. A tree can be having one vertex and no edges. So it has one vertex and zero edges. This will also be referred as a tree. This has two vertices and one edge. This is also an example of tree. When you have 3, 1, 2, this is a tree. How you can draw this in different ways? You can bend it and then you can draw it in this way. So it is connected and it doesn't form a circuit. 1, 2, 3, 4. So this is also a tree. Okay. So 1, 2, 3, 4. This is going to be a tree with 4 vertices. Okay, in all the cases we see that you are able to reach from one position to the other position by a path which is an alternative sequences of vertices and edges, and you don't have any closed quantity, closed path, which we refer it by the name cycle or circuit. You don't have a cycle or circuit, in which case all these things are now referred as trees. Okay, so we are now seeing the definition of tree. Tree is a graph that is connected and circuitless. Next, moving on, what is going to be the basic property of a tree? A basic properties of a tree is that an undirected graph, that is, you don't have any directions in this graph, will be referred as a tree if and only if, so this becomes necessary and sufficient condition, if there is a unique simple path between every pair of vertices. Between every pair of vertices, there is going to be a unique simple path. So what do you mean by this uniqueness? There is going to be only one path available, and you have it to be a simple path from every pair of vertices which is available. What happens if there are going to be two paths? Now if I am able to move over here from D, B, E, G, as well as there is going to be one more path where I can move to my G from D, like from D I move to something called as I, and a J, and then I am able to reach a G. This has two paths. One path from D to G is going to be this way, and the other path is going to be this way. So if there are going to be two paths, what will happen? Automatically we see that the tree is developing a circuit. So it happens that you cannot have two paths. The path which you have is always unique. So you can reach between every pair of vertices in a unique way. So this is what is going to be the necessary and sufficient condition for a graph to be called as a tree. So a graph will be called as a tree, or a tree can be called as a graph if and only if there is going to be a unique simple path that is going to connect every pair of vertices. The second and important property a tree holds is that whenever a tree has n vertices, it has n minus 1 edges. So it has 1 less than the number of vertices. We can see for ourselves 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 vertices over here. Let us count for the edge. 1, 2, 3, 4, 5, 6, 7. So how many edges it has? It has 7 edges. Over here also we see it has 1 vertex and 0 edge. N vertices and n minus 1 edges. This is true for all the case. 2 vertices, 1 edge. 3 vertices, 2 edge. 4 vertices, 3 edge. 1, 2, 3, 4, 5, 6. 6 vertices, 1, 2, 3, 4, 5. 5 edges. So the basic property says that a tree with n vertices has n minus 1 edges. So we will have to keep these two properties in mind whenever we are constructing a tree out of a given graph G. The next concept which we will be looking on will be called as spanning tree. What do we mean by a spanning tree? A subgraph of G that contains all the vertices of G, and furthermore if it is going to be a tree, that is, it is going to be connected and it is going to be circuitless, then this subgraph of the G will be referred by the name spanning tree. So what do we do is we retain the vertex set of G. Retain the vertex set of G. So if this is going to be my given graph G, A, B and C are going to be my 3 vertices. I retain the 3 vertices as such, A, B, C as such, and I know that there are going to be 3 vertices and I need to form a tree out of this. So if I need a tree, I just now saw that a tree with 3 vertices has 3 minus 1, so it has 2 edges. So how to construct the various possible ways? So I can have this edge and this edge, so this will become a tree. I can connect this edge and this edge, so this will become a tree. And I can say we are connecting this edge and this edge, and here also it becomes a tree. So these possible combination where I retain the vertex set as such and I am constructing a tree out of it which satisfies a connectedness and circuitlessness will be referred by the name spanning tree. So a spanning tree has all the vertices of G and furthermore it is going to be a tree. Next we will have one more example to see what is meant by a spanning tree. Say suppose we have a graph G which has 1, 2, 3 and 4. Okay, vertices are going to be 4 in number and totally 1, 2, 3, 4, 5. You have 5 edges in your graph G. Okay, I need a spanning tree out of this G, which means I will retain my vertex set. So if I retain my vertex set of G, 1, 2, 3, 4, this is retained as such, and I have 4 vertices, and so my spanning tree will have 3 edges. I am dropping 1, 2 edges from my graph G, so that will become a subgraph of your G. And now the construction has to keep in mind, it is going to be circuitless and it is going to be connected. So how can I do it? I need 3 edges. Let us start adding 1, 2, 3. So this is going to be a spanning tree. Next, let me add 1, 2, 3. This is going to be a spanning tree. Next, let me add 1, 2, 3. This is going to be a spanning tree. Let me add it as 1, 2, 3. This is going to be a spanning tree. Okay, 1, 2, 3. This is going to be a, okay, now 1, 2, 3. So let me have it as, we have already done this. Control. Okay. Yeah, this is going to be one more spanning tree which we have not taken a reverse copy of it. Okay, so in this way we will be able to construct so many spanning trees from a given graph G. So you will have to keep in mind vertex set is retained and the properties are tree, that is it has to remain connected and it has to be circuitless, and it with n vertices it must have n minus 1 edges. These things are kept in mind. The next concept we move on is going to be called as minimum spanning tree. What do we mean by minimum spanning tree? Say suppose we have been provided with a weighted graph. What do we mean by a weighted graph? Is a graph that contains numbers on its edges. These numbers are referred as weights. Now the problem is to find the smallest total weight of the spanning trees of your G. Say suppose this is going to be a copy of my spanning tree having weights on its edges. Let me have mark some weights on these edges. So say suppose I am going to have it as your A, B and C. So this edge is going to have weight to be equal to 2. Let me have weight over here to be equal to 3, and let me have this to be equal to 4. So I am giving various weights to my edges. So in which case you call this to be an weighted graph. Okay, now the possible spanning trees for my graph G will be copy number 1 this, copy number 2 this, and copy number 3 here. Okay, 3 sets I have. So I can say suppose now this is going to be my 2 over here and a 3 over here, a 2 and a 3. So what will be the weight for this spanning tree? 2 plus 3. So this weight will be 5. Now if I have a copy of 4 over here and 2 over here, what will be the weight? It will be 4 plus 2, 4, 5, 6 over here. So this will have a copy of 4 over here and a 3 over here. So the weight will be 4 plus 3, which will be equal to 7. Now what we are interested is the minimum spanning tree. What do we mean by minimum? The weight is going to be the least, in which case which graph has the, which spanning tree has the least weight? This one. So this copy where it goes from A to B and B to C with edge weight 2 and edge weight 3 is going to be called as the minimum spanning tree for the given weighted graph called as your G. So this is going to be an important point in your optimization problems where we need to maximize the profit and minimize the cost for transporting any goods from a source to a destination. So or it can be, these weights can represent the time units required to move from a particular source to a particular destination, and we need to minimize the time taken for our transportation or for the movement. In which case the concept of minimum spanning trees is going to be of prime importance for any networking system. So this is being a small graph, We are able to make copies of the subgraphs easily and then find out manually what is going to be the weight of these, and then find out which is going to be the minimum spanning tree. But when we are having a really complicated or a big network or a weighted graph, then finding all the possible spanning trees out of it and finding which is going to be the minimum out of them is going to really turn out to be a complex job. So to ease with it, there is something called as Kruskal algorithm devised, which will help us to find the minimum spanning tree using an algorithmic process or a step-by-step process. The concept will be covered in the next video. Until then, keep learning, happy learning. Thank you very much.